We have done previously, we have been looking at Hess's law cycles. We've done Hess's law cycles for formation, combustion, and average bond enthalpy. They have tended to be 2 or 3 step cycles. We've not done any multi-step cycles. And what we can think about for Born-Haber is that the Born-Haber cycle is merely an extension of Hess's law. If you remember, Hess's law is just talking about the energy difference between the reactants and the products is independent of the pathway taken. The magical quantity we're looking at calculating using the Born-Haber cycle usually is the lattice enthalpy. Okay. You will recall that the definition of ionic bonding is the electrostatic attraction between oppositely charged ions, and this particularly refers to the ionic crystal lattice. Remember, things like CaCl2, MgO, LiF are basically empirical formulae which are describing the giant ionic three-dimensional lattice of oppositely charged ions. So make sure you've got that picture in your head, because this lattice enthalpy measure is measuring the energy that's holding that crystal three-dimensional lattice together. Okay, so start with some definitions where we always begin. What is lattice enthalpy? Well, lattice enthalpy can be defined in 2 ways. It can be when 1 mole, here is that lovely, you're doing your enthalpy and your entropy and your lattice energy calculations, always just put 1 mole. You're going to get a mark. Okay. When 1 mole of an ionic lattice, remember it's 3-dimensional, is formed from its isolated gaseous ions. The IB are happy for you to say that definition. That's okay. You will also see in the IB syllabus that these gaseous ions, in this case Na plus G and Cl minus G, are at what's called infinite separation. So they are at infinite separation. What does that mean? That means that there are no attractive forces going on between them, because as soon as these come close enough together, they are going to form the solid. Now, this particular definition, where we're going from the gaseous ions to 1 mole of the solid, is bond making. It's bond making. So this is an exothermic process. So we would expect delta H to be negative for this definition 1 for the lattice formation enthalpy. Clearly this is formation, Na plus G plus Cl minus G go to Na plus Cl minus S, just common salt, which you are familiar with. The IB don't care which way around you do it. You can also go, as well as from the gaseous ions to the giant ionic lattice solid, you can begin with the solid and end up with the gaseous ions. Now, this is bond breaking, so Na plus Cl minus, we are breaking the bond between Na plus and Cl minus ions, and we are forming the gaseous ions at infinite separation. Okay, so here infinite separation to forming the giant ionic lattice, which is bond making, exothermic, and here's the giant ionic lattice being broken down into the gaseous ions at infinite separation, which is equally endothermic. So if the top line was minus, 1,000 kilojoules per mole, the bottom line would be plus 1,000 kilojoules per mole. Any questions at this moment in time? Lucas has raised his hand. Yes, Lucas.
I just wanted to ask, so what makes this different from just the latent heat of fusion and latent heat of vaporization?
Latent heat of fusion and evaporation are specific terms that we're going to be using, that you can use in physics. You can use MC delta T to calculate those. You can't use MC delta T to calculate this. You'll perhaps see when we do the cycle, Lucas, the roots data that goes into forming this quantity. Okay, So this is a chemical, using chemical reactions to get a chemical quantity. The heats of vaporization, etc., they're physical quantities that we get from physical measurements. Does that make sense?
Okay.
There is some similarity, and I'm glad you pointed that out. What separation does the lattice have, says Joseph. Joseph, could you explain further? The lattice itself is not separated. The lattice itself is that giant ionic lattice. So if we look at sodium chloride, it's got the coordination number of 6. I think I've held this up before for you in the laboratory. And it looks something like that. Okay, Cl minus are going to be the big ones because it's gained an electron. Na plus are going to be the small red ones because they have lost an electron. What separation does the lattice have? The ions in the lattice. The ions in the lattice, once they are bonded, are as close as they can possibly get without falling into each other. So it depends actually on the ions that are there. If it's a 2+, it's going to be a bigger charge, so it's going to be a shorter distance. If it's 2-, again, it's going to be a bigger charge, shorter distance. But we're looking at that energy. We're not looking at the distance. We're looking at the energy of the lattice, Joseph. Make sense? Okay. Oh. Is that OH or OK, Joseph? Very good. Any other questions? So we're just on the definitions at the moment. Infinite separation, gaseous ions, 1 mole of the gaseous solid. It's the solid, sorry. And the IB don't really care which way round we do this. You can do the exothermic bond making, or you can do the endothermic bond breaking. Both answers would be acceptable on the mark scheme, -1,000 or +1,000, whatever it happens to be. We'll both get the full marks for this. Okay. So, 1 mole, isolated gaseous ions. It is very exothermic, because you'd expect these gaseous ions coming together and fusing is releasing a lot of energy. And here we have what we are used to, exothermic, where we have the products at lower energy than the reactants. Here's the reactants, and here's the products. Here's the lattice enthalpy, by definition. Gaseous ions, infinite separation, 1 mole of a solid. Okay, we're going to have the opposite direction, which is not highly exothermic, is now highly endothermic, because now we are breaking the bonds, and the bonds in sodium chloride and any ionic lattice are really, really strong. So it's going to take a lot of energy to pull them apart. So we can't measure it directly, so guess what? We're going to be using Hess's law, and a particular form of Hess's law, which is called a Born-Haber cycle. Now, the greater the charge density, that means 3+ is bigger than 2+ is bigger than 1+, the greater the attraction. As I was just saying, the bigger the magnitude of the charge, the larger the lattice enthalpy. The bigger the charge, the larger the lattice enthalpy, because a 2+ will attract its anion twice as much as a 1+ in a lattice. That means bigger charge is probably going to have a higher melting point. You can take it to boiling eventually. You can boil a diamond if you really want to. Solubilities we're not going to cover today. That's a separate lesson, and that's looking at the relative hydration enthalpies with the lattice enthalpies. But if you get the idea that the bigger the charge, the stronger the lattice, that means the higher the melting point. We can look here, we've got our standard group 1 and a couple of group 2 metals on the left-hand side. At the top we've got our halogens and some oxygen, oxide ion. And what can we see? We can see that as the cation is getting bigger, then the magnitude of the lattice enthalpy is increasing. 2+ is 2,000 over 2,000 kilojoules per mole. It's in kilojoules per mole, always kilojoules per mole. And the 1+ are a third as much, 6, almost 700, 800 roughly. So the magnitude of the charge is having a massive effect on the cation. What about the anion? Well, we're going from our halogens here, kind of stepwise. Okay, these are just going up here because that nucleus is more exposed. Remember that from your periodicity. And then oxygen's more than double, 3 times as much for O2 minus, for the lattice enthalpy. So smaller will have greater attraction because of their higher charge density. Don't forget that as it loses more electrons, the first, the second ionization energy to get the 2 plus, that atom, the ion, is getting smaller and smaller because of the ratio of the protons in the nucleus to the electrons going around the outside. And that will continue to 3 plus, 4 plus, etc. So the point of this slide is the bigger the charge, the bigger the lattice enthalpy, because the smaller the ion. Okay. Here we have Na plus Cl minus. Sodium has the same charge as potassium, but it is smaller. Why is it smaller? It's higher up in group 1, less shells. We know this from periodicity. So let's have a look at our first Born-Haber cycle for sodium chloride. Okay. There will be some familiar pieces of information in here. Certainly the top one, enthalpy of formation of sodium chloride, and enthalpy of formation. The definition of enthalpy of formation was what, Guy?
It's the enthalpy change when forming 1 mole of a atom molecule
From
its element
in their
standard form, standard pressure.
In their standard states. Very good, Guy. Well done. So the top one we are familiar with, enthalpy of formation. We have seen this before. It's in the data booklet. You can look it up. Now, I did mention during the standard level material that there were other enthalpies that we need to be aware of. So here we have sublimation. Remember, sublimation is solid to gas, so the energy required to take sodium in this case from solid to gas. And solid to gas, I have to put energy in. I need to overcome those inter-atom forces, and it's going to cost me 108 kilojoules per mole. Atomization, what's atomization? Atomization is when we have, a monoatomic anion, so like NaCl, Ki, CSF, etc. And we know that the halogens are all diatomic molecules, so they exist as Cl2, F2, but we only want 1 chlorine in 1 unit of NaCl or Ki or CSF. So we have to use half of that, and that's plus 1 to 1 in this case. Ionization energy, we've done that before. 1 mole, gaseous, 1 mole of electrons. So ionization energy, we are breaking the bond here, we're breaking the bond between sodium to make that sodium ion, sodium 1 plus an electron. And electron affinity. Electron affinity, you can see here that there are 2 of the enthalpies which are exothermic. 2 of the enthalpies are exothermic. That will be on a question I'll be asking you in about 10 minutes' time. And 3 of them are endothermic. Now, given these, we can work out the lattice enthalpy of sodium chloride. Now, this is Na plus G, Cl minus G, NaClS. So these 2 are bonding together, so they're coming together. So it's exothermic, releasing energy. And we can use these 1, 2, 3, 4, 5 preceding enthalpies to work out the unknown lattice enthalpy. Now, are you ready? Setting up a Born-Haber cycle. We always begin with the enthalpy of formation. So 1 mole of a compound from its elements in their standard states. We need half a Cl2 because there's only 1 Cl in NaCl. We know that this is bond making, so it's exothermic, so the products have less energy than the reactants. And sodium chloride has a low enthalpy in the elements, which is measurement, so it's minus 411 kilojoules per mole. So we would write in here minus 411. Now, we're just using Hess's law principles. Energy difference between reactants and products is independent of the pathway taken. So I've got my Na solid and my half Cl2G. And I want to eventually end up at Na plus G and Cl minus G, because that was lattice enthalpy definition. So what we're going to do first, well, this one has taken sodium and has sublimed the sodium. It's gone from sodium solid to sodium gas. And that is endothermic because we have to put energy in to overcome those forces of attraction. And the value is plus 108 kilojoules per mole. So you can see this is the start and this is the end of the arrow. This is the start, this is the end of the arrow. And what we're doing is we're building up a picture. What has happened here? Let's go back 2 steps. Na plus half Cl2G. What did we do? NaS went to Nag. Nag, Cl2 stayed the same. It did not change. NaS, Nag. This is what's changed. This is exactly the same. As the sodium got into a position that we can abide by or we can satisfy the definition for lattice enthalpy? No, not yet. Chlorine, we also need to get to 1 atom of chlorine. So we sublimed our sodium, in this case, solid to gas, and we've atomized our half a molecule of chlorine to make 1 atom, hence its enthalpy of atomization, 1 atom of chlorine. Okay. We are now going up. Why we're going up? Because we had to put energy in to break that bond. I know it's half a chlorine bond, which is a bit bonkers, but Cl to Cl, you're breaking that bond to make 1 Cl. So theoretical. Next, we need to ionize our sodium because the definition for lattice enthalpy was the gaseous ions at infinite separation on 1 mole of the solid. So first of all, we have taken our sodium and we have got it gaseous. We've got our chlorine gaseous. And we now have ionized our sodium. We all know the definition for first ionization energy. And now we are adding an electron. Why has this gone down in energy? That's because it's exothermic, because we're adding an electron. It's the electron affinity. So Clg plus E minus, making Cl minus G is the definition for electron affinity. Now we have our Na plus G and our Cl minus G, and that will give us our lattice enthalpy. Aha! We now have built a bit more elongated, not overly complicated, a bit more elongated Born-Haber cycle for sodium chloride. Where did we begin? Well, we began here. We had our standard states. This was definition of enthalpy of formation, process 1. Sodium is normally a solid, chlorine is normally a gas, and we make solid sodium chloride. That's exothermic because they are bonding. They're coming together, they are bonding, and that's exothermic. This is exothermic, lattice enthalpy, but it could also be endothermic in the opposite direction. The only other exothermic process here was this one, which is the electron affinity. Now you can see that we can put the numbers in. What do you mean we can put the numbers in? Well, if we take the numbers that are given in the presentation, and we can follow the cycle around. So we could say 2 plus 3 plus 4 plus 5 plus 6, equals 1. So enthalpy, I know that says 6, I'm doing 1. Enthalpy of formation equals, just add everything up, because you just follow the cycle around. Start, end, start, end, start, end, start, end, start, end. Wash. 1 equals 2 plus 3 plus 4 plus 5 plus 6. But if I want 6, then I'm going to have to go around this way, aren't I? So it's going to be against the flow of this. So that's not plus 5, that's minus 5. Against the flow of this, minus 4. Against the flow of this, minus 3. Against the flow of this, minus 2. With the flow of this, plus 1. So 6 equals, going around this way, minus 5. Minus 4, minus 3, minus 2, plus 1. Common errors. Because we are going minus 5, they'll think it's minus, but it's minus a minus, so it's a plus, right? And then each of the individual energies will have a plus or a minus. Clearly, the minus 3, 6, 4 which is the electron affinity, and the, where is the other one? It's the 411, which is the enthalpy of formation, will be negative. The rest will be positive. But whether you're adding or taking them will depend on their position in the cycle. Now, sodium chloride is a pretty straightforward cycle, because when we add one electron, yes, it is bond making, it's exothermic. Often when we add the second electron, there's electron repulsion, and we have to overcome that energy, and often it becomes endothermic for the second electron affinity. We'll see that shortly. So I think it's important to just have a quick meditate on here about what we're actually seeing as our first Born-Haber cycle. Right, that was sodium chloride. Do we have any questions at this moment in time? I'll put that back on the screen. Please shout up. Please put your mic on if you've got any questions. Or type in if you are shy. Okay, this is a standard textbook way of displaying a Born-Haber cycle. There is another way to do a Born-Haber cycle. Do you remember where we put the enthalpy of formation here? Process 1, gaseous, solid, solid, exothermic process coming together. We can also make that, we flip that through 90 degrees, we can make that the top line of our Born-Haber cycle, which is what we've done here. Now, lots of chemists prefer to do it this way, I am one of them, rather than doing it in that way. But this way tends to be 3/4 of the time how they present it in the exam type questions. This way, why do I like this way? Well, formations at the top, I start with what I know, enthalpy of formation. You can obviously get that from the data booklet if you need to. But the thing I like about this method is that we do it sequentially. So I take this potassium and I go from solid to gas, and then that is the enthalpy of, what's that enthalpy of? Solid to gas. Those being shy, obviously it is
sublimation.
Yay! Well done, sublimation.
Are you sure you didn't get my email?
Ollie, I am recording this.
I
Do you want, while you're on?
I put a lot of effort into it. Sorry?
I will check now. Oh, yes, 8:23. Yes, that's why I've not seen it.
Okay.
Oh my gosh. Oh, you want Richard Thornley to join you? Oh, sorry, it's only Mr. M. The third installment of Peter Jackson's Middle Earth Saga. Get well soon, Ollie. Thank you, Ollie. Thank you. Right, Ollie, since you're on, you can answer the rest of the questions now. So what's this? What's this process here?
That's the first ionization energy.
Good man. What's this process here? Half Br2L to Brg.
Vaporization. Atomization.
What?
Okay.
What needs to atomization? And this one is
atomization.
Yeah. And this one.
The electron affinity.
And this one.
That is the lattice enthalpy.
It is the lattice enthalpy. And in this case, we're going from the ions to the solid. So is that exo or endo?
That is, wait, don't tell me. Actually, we'll get this.
I'm not going to tell you.
That exothermic.
It is exothermic in that direction. Thank you, Ollie. Well done. Now, we can see here that all of this flow. I'm showing my fingers on the screen. That's not going to work. Let's use the pointer. All of this flows in the same direction. So if I add all of these together, that will give me the enthalpy of formation for potassium plus half a bromine, making potassium bromide. Okay, so I could be given delta HF. I could be given any of the 1, 2, 3, 4, 5 out of any of these 6, and be expected to work out for the unknown, whether it's ionization energy or electron affinity, atomization, enthalpy of formation. Any of them can be unknown in the cycle. Okay, so I prefer this method. It makes sense. Solid gas ion, liquid gas ion. Done. We've got the gaseous ions. We've got the solid. Enthalpy of formation, standard states. Bosh, you're off. Okay, but the exam will give you it in that manner most of the time. Okay. My mind is slightly blown, Joseph. I'm glad. That was my intention this morning. My lesson plan is always blow their minds. Okay. So a few cheap.
Mr. Mitchley.
Yes.
Sorry, I just wanted to ask. So with the bromine, is it still atomization, even though the state is also changing from liquid to gas?
Yes, it is. What would you like to call it? Because I can think of at least one other way to label it. What do you think it should be, Lucas?
I don't know. I just thought that the chlorine was gas when it was half Cl2 as well.
Ah, but that was its standard state, wasn't it? So enthalpy of formation standard states. Bromine standard state, room temperature, is liquid, and chlorine is gas. So it was already gas going to gas, but this is liquid going to gas. You've atomized them both, because the atomization term refers to breaking half of a theoretical Br2 molecule, but clearly you can't. It's a theoretical, right? It's half of the Br2, so you're making it one atom of Br rather than half a molecule of Br2. That's what the atomization refers to.
Okay.
Lucas has gone quiet. Is that okay?
Yep.
Cool. Then you've got electron affinity, ionization energy. So what value do you get for the enthalpy of formation? Go. Type your number into the chat, please. What's the number? Who's going to be brave and type their number into the chat first? Oh, I didn't get that, Kristen. Put it back on the screen. I got what Ollie got. Excuse me. Yeah, I got that. So why is it 1632?
Could you please put the screen back up?
Yeah,
please?
sure.
Thanks.
So what you're working out here is the enthalpy of formation. Okay?
Guy has a question.
Yeah. So
How come the electron affinity value isn't negative?
it should be, but all we can use is the data as given. So there's no negative sign, so I'm just assuming it's positive. You will see, is it in the next one? I'm going to show you another one in a minute where the electron affinity is positive for the second one, I think. Yeah. Okay, so all you can use is the numbers as given, Guy. So here, there's no negative, so all of this is positive, so you're just adding them all together. Okay, maybe Kristen, did you add the negative for the electron affinity and the enthalpy of formation? Maybe that's how you got the answer.
Yeah, I thought the arrow goes the other way.
Yeah, I see. Okay, no worries. No worries. It's all practice. So all you can use is the data as given. So there are no negative signs there. So it's just for this one, the unknown, summing the rest of the values in this differently orientated Born-Haber cycle. Any more questions? Okie dokie, Joseph says. Very good. So, state the names of the enthalpy changes C and D. What is enthalpy change C? We've just done that, it's atomization. What's D? Typing in, aren't you? What's D? Well done, Shimei. D is the, somebody say it please, for the sake of my sanity in the lesson.
Electron affinity.
Thank you. And Joseph, define electron affinity. Go. Smiling. Okay, 7 seconds is up. I've lost the will to live. So, deduce which of the two enthalpy changes, A to E, have negative signs. Which two have negative signs, please? Or should have negative signs, but don't in that cycle.
E and D.
Very good. What are the names of those? What's the definitions of those letters, please, Ollie?
So D, electron affinity, was the energy released when 1 mole of gaseous ions gains an electron to become 1 mole of gaseous atoms.
Beautiful.
And then the E represented the lattice enthalpy of the potassium bromide.
Infinite separation,
so
gaseous ions. Yes.
Yeah.
Beautiful. Thank you very much. Determine the value for the enthalpy of formation. We've done that. Now, in the data booklet, it will give you, there are tables of lattice enthalpies, okay? And if there is a difference, which there will be, when there is a difference between the lattice enthalpy in the data booklet and the calculated lattice enthalpy, that's going to tell us about the ionic character of the lattice, whether it's more or less ionic, depending on the difference between the calculated and the theoretical, but we'll save that for a future lesson. Explain why, we'll just have a look at that. So, the final cycle I wanted to share with you is, as I said, NaCl is monoatomic, it's Na plus Cl minus. But what happens when we have a divalent cation, which is a normal case? So here we have MgCl2, or here we have the Born-Haber cycle for MgCl2. It wants the lattice enthalpy. Lattice enthalpy. Mr. Chakramakal, which number is the lattice enthalpy on that Born-Haber cycle, please?
7.
It is number 7. Well done. We have electron affinity, but now we've got times 2. We've got 2 electron affinities because we need to have 2 electrons, 1 to each of the chlorine atoms. Oh my gosh. So here we have enthalpy of formation, magnesium solid, chlorine gas, MgCl2 solid. 1 is enthalpy of formation. What do we do here? Solid to gas. Solid to gas. So that's going to be the sublimation. And then 3, we're going to atomize the chlorine. But now it's Cl2 to 2Cl. There's none of that half Cl2 nonsense because it's MgCl2, not NaCl. Okay. Now we've got a gaseous atom. Then we're going to take away our first electron, that's our first ionization energy for magnesium. And then staying with the magnesium, we're going to take away the second electron, which is the second ionization energy for magnesium. And now we need to attach one electron to each of these chlorine atoms. And now we have our infinitely separated gaseous ions and our ionic solid, which in this case is MgCl2. So now we've got some doubling to think about depending on what the formula is. If I was in the class right now, I would be asking you to draw the Born-Haber cycle for aluminium oxide. Because aluminium will go Al, Al1+, Al2+, Al3+. Oxygen will go O1-, O2- until you got your O2-, Al3+, 2 and 3. And there's quite a bit of mathematical shenanigans that you need to do to make that one work. Now, you've seen NaCl, a quick tour of MgCl2, and you've also seen the KBr set out in a slightly different manner. So, what I'm going to guide you to do now is if you go to classwork in our lovely Google Classroom, you will find a problem set, and this is called Born-Haber cycle problems. Now, here we have all of the data that you need to work out the answer, and crucially, the answer is given, so you can check if you are correct. And there are quite a few to keep you occupied. Okay. So, that was Mr. Emphakhem's introduction to Born-Haber cycles. I bet you're really glad I joined this morning's lesson, aren't you? Right, guys, questions, fire away, please. Just 25 + 9 already. Electron affinity, electron affinity. Yes. What's the question? What's the question, Shumei and Joseph, please?
Mr. Midgley.
Yep.
So, was what we did last lesson with Mr. Gardner all there is to entropy in this topic?
I don't know, Lucas, because I wasn't there, mate. Sorry. Did you do delta G is delta H minus T delta S?
Yeah, but we didn't do any example calculations. We sort of just looked at it.
So I would say no. I'd still say there's quite a bit to do on entropy. You just done products minus reactants, yeah?
Yeah.
All right. So that yeah, it's just a Hess's law cycle like you used to. So that's fine. That's great. But then delta S is, did you do the delta S is in joules per Kelvin per mole, and then the rest of the terms in the delta G equation are kilojoules per mole. So you have to factorize by 10 to the -3 to get it to
Yeah, he did mention that.
Right. Did you talk about exothermic, endothermic at low temperature, high temperature, magnitude of the temperature, and whether it would be spontaneous or non-spontaneous?
Yeah.
And did you do critical temperature? So what temperature a reaction becomes spontaneous?
Yeah.
You did. Okay. Sounds like you've done quite a bit then in one lesson. We'll go back to it and review it as well, Lucas. But it sounds like you covered most of it. Yeah. Okay. So I wanted to leave you with this one, and this one is magnesium oxide, done in the old style. So we can see that the magnesium goes solid to gas, so it's atomized. The oxygen is atomized, half O2 to O, that's all good. First ionization energy magnesium, second ionization magnesium, Mg, Mg+, Mg2+. But then the first electron affinity is -141, so it's exothermic because we're adding. But the second electron affinity, as I was mentioning, is +798. So that's costing me a huge amount to add that second electron. We're having to fight that electron to pair up with that first electron which has been added. So the second one is endo, and the first one is exo. So be careful on your electron affinities. That's why I was cautious when I was saying it should be negative or positive. It can be, particularly when it comes to the second and even third, if you're going there, positive rather than negative, because you're fighting to get that extra electron into the atom. Okay, so always take the data as given. It will either give you it in the question, or it will guide you to the data book, and the data book that will have the minus or the plus next to it. Right. Hopefully that's your mind's blown. NaCl KBr, MgCl2, and MgO in half an hour. How are you feeling? Good? Okay, over to you now, guys. Now, Miss Pooja is a wonderful chemist, and she's going to look over your shoulders while you are having a go at these ones. Okay, so start having a go at the Born-Haber cycle problems and see how you. I think you'll get the first one done and get the -3,380. See, it's got the negative signs in here for the enthalpy of formation. That looks like it's a plus there, and hopefully you get the correct answer. Okay, questions? Fire away. All good?
May I go grab some food from my locker, sir? I'm starving.
You're asking if you can take food. I'm leaving that on the video. That's gonna make the edit. That's gonna make the edit. Can I have some food, sir?
But like, may I? I'm actually dying.
I don't think you are, Ollie. I think it takes 3 minutes without oxygen, 3 days without water, and 3 weeks without food. When did you last eat?
4.
4 a.m.
Yeah.
Well, you did write a fantastic email. And can you make sure that